To implement Langton's Ant algorithm, we need to use pygame, in addition to a couple of parameters that are going to be essential in order to give proportions and dimensions to the two-dimensional grid. Because this is an introduction to the concept of cellular automata using two-dimensional grids, it's going to be important that we go through the general process by which we can draw and code things using pygame. So the first thing we're going to need is a resolution for the tiles. Because our tiles are squares, we're going to need the same width and the height, so we just need one scalar. In the dimensions, we're going to have an iterable object that can be a tuple or can be also a list that is going to contain how many columns and how many rows our board is going to have. The screen is a parameter that transforms the number of columns and the number of rows into values of pixels so that we can create a screen. The next line, line 15, sets a variable called display that represents a pygame surface. A pygame surface is a special compound object that is gonna contain a screen that is gonna represent the screen where we can render our animations. So to create it, we're gonna need to use the sub-library display and the method setMode, which receives a two-dimensional structure representing the width and the height in pixels. It is important to notice that the components inside of a screen are integers, because the basic unit of visual information is a pixel. The next one is going to be the frames per second, how fast the animation is going to go. Now, pygame, like many other pipelines or video game engines or libraries, has the ability to, use a particular value as a reference. However, at the end of the day, it all comes down to the performance of the machine. So even if we set 120 frames per second, if the machine cannot handle that number of frames per second, it's gonna do the maximum number that it can do. So this doesn't really, burn any additional memory. So in the data definition sections, we have the basic unit of information in this program, which is the tile. The tile is a compound data type of type class, a class with the same name, that receives two components. Here it says 3, that's an error. And it is gonna be each of the pieces that make the board. The class tile receives at the beginning in the constructor two elements from the outside world called X and Y, which represent the number of columns and the number of rows. Now, something that may be easier to understand is actually to change it to C and R, because really that is what these values that enter the matrix are at the beginning, C and R. So these ones are going to be the value of cell.C and the value of cell.R, which means that we need to move these two elements down below in order to have them ready whenever we need to use them. So C and R represent integers that map the dimension, the parameter called dimensions, right? It's going to go from 0 to 159 in the columns and 0 to 159 in the rows. Now this X and this Y represent the transformation of that particular column and that particular row into pixels. Then we have a structure known as rect. Rect is gonna create a two-dimensional rectangle that we can actually visualize. It's gonna fill its pixels with colors, are the boundaries of our tiles. And it receives the position in X and the position in Y as the top left corner of that rectangle, or in this case a square. And then how wide and how tall that rectangle is gonna be. Because we use the same parameter, which is the dimensions of that rectangle, we know that this is a square. In line 28, we specified that the position X and Y in the coordinate system is going to be the top left corner of our square. And then we have the state. The state is going to be the value that represents the color of our tile. The functions that this tile has are two. Draw a square is in charge of drawing the rect component, which is this one, in the display, which is the Python surface that we generated. getColor is a helper function inside of this class in charge of mapping the integers into colors. The next data definition is a compound data definition that fits on the tile. It is an emergent property itself. It is the combination of multiple tiles to form a row. And that's why we use procedural generation. You can see it here using range and the parameter number of columns in order to generate in each of those steps of the for loop one new tile and appending that new tile inside of the row of tiles. But we don't stop there. This generates a one-dimensional array. We need to create an array of arrays, and that we're going to call the grid. So in the same way that we generated the rows procedurally, we are going to generate the grid procedurally. Pay attention to this for loop right here that uses as the loop variable the letter R, which represents the number of the rows. For each of the rows from 0 to 159, we generate a new row. And then we simply copy and paste these elements, the ones that belong to the previous data definition, which is the tile row, and nest it down here. You can see that copying and pasting returns the exact same values that we had before, except for this element right here. This 0 right here should be changed to R, because it's not always going to be the same row 0, right? This time it is inside. It's been procedurally, the rows are also procedurally generated. And finally, we append to the grid. We append the tile row. The next data definition, which is called the current ant, simply represents a position from a tile in its grid. Here you can see that the variable called CA is defined as the coordinate in the rows and the columns of a particular, of the center of that grid. And finally, we have the direction data definition. This data definition is global because there is only one ant and is represented by a one hot vector, which means that it is an array of 4 integers represented as binaries, where the only one that exists in that array at any given time reflects the position of the ant in the world. So in this case, the order is given by the index. If the 1 is in the first position, then that is right. Then if the second position is down, then left, and then up. You can see the diagonal movement. And the reason why we represent changes in direction in this way is because adjusting the direction in a clockwise fashion is very easy to do. We just need to find the current index of this particular direction. And then we need to add 1 to it. Add 1 to that position, and that is going to become the new direction in a clockwise fashion. Take as an example the right direction. We have the number 1 in the index 0. We add 1 index, and we move the 1 to that new index, and that is going down. Going in a counterclockwise direction is a reverse process. From down, we subtract from the index, and we end up at this position, which would be right. From down to right is moving in a counterclockwise fashion. We are going to start this program by first setting the direction to a general case, which in this case is going to be a copy of the direction R. The reason why we use the method list in this case is to clone the object called dir, so that these lists of here represent a reference on which we can use conditions with if statements, and this one will be the actual current direction in which the ant is moving. The next element has to do with how pygame is wired. The pygame library requires you to have 2 functions called draw and update. The draw function is going to be in charge of simply pasting and rendering the pixels every single frame inside of your screen, which we call the display. So we're going to start by adding a color to this display, and the color should not matter because the entire screen is covered by a tile. By our tiles, our 2-dimensional grid. However, if we see any background that is of this color, we know that something may be going wrong. We are gonna need to traverse the 2-dimensional grid, asking every single tile to get rendered. To do that, we use a 2-dimensional for loop. Now, whenever I work with data definitions, which are the first step in making a good program, we also usually generate a template. This two-dimensional structure, this two-dimensional for loop is the one that we're going to be using by simply trusting that the template is well formed, and this answers the question, how can I go through every single tile? Now that we have the tile, we just need to specify what is that thing we need to do to that tile. What we want to do to every single tile is to draw it. So we're going to access the method that lives inside of this instance of the class, and we're going to call the helper function called draw square. The last step of the draw function involves asking for a handshake to the real programming language that is in charge of rendering the pixels in the screen, because Python doesn't really have that capacity. We're going to call the pygame library, the sub-library display, and the method flip. The next thing we need to do is to make sure that we have a mechanism to call these functions. We're going to call this forever, and we're simply going to draw and update every single frame. Before we run this, we also need to make sure that we have a way to exit the program on command. That means closing the window. For every single event in the pygame event system, using the method get, we're going to ask if the event is of type pygame.quit. And if the answer is yes, then we can exit the pygame library using pygame.quit. This is going to allow us as well to click in the windows and going back and forth between applications without the program collapsing. So let's run pygame and let's see if this yields any results. And there it is. You can see this window that is entirely white. If the background is supposed to be gray, which is the same color of VS Code right now, how come I don't see any of it? The reason is because the program is well formed, and every single space, every single pixel inside of this two-dimensional matrix is covered by a pixel that belongs to a tile, is covered by tiles. So let's close this window and let's keep moving. Now we can focus on the actual algorithm. We're also gonna register the dir variable as global so that we can modify it within the function. Remember that variables defined inside of a function can only be modified locally. By assigning the global reference, we say that the name of the variable that we want to modify is global. We are gonna call two helper functions. So here we need to follow our algorithm. We are gonna divide the program in two helper functions. The first one is gonna be called update tile, and the second one update direction. Those are the two main steps in Langton's Ant algorithm. Let's generate the first method. We're going to place it right here. And the purpose of this function is quite straightforward. It's going to handle the states of the current tile, and it's going to change it from 0 to 1 or from 1 to 0. So here we're going to need to ask a question using an if statement. We're going to ask if the grid at the position of the current ant's location in R and the current ant's position in C, that is just one position in the grid that just happens to be where the current ant is located at this point. Therefore, because this is just of data type tile, we can access its states. And we're going to ask if this state is 0. If the answer is yes, well, we just change it to 1. Otherwise, it means that the state is 1, in which case we change it to 0. That is the first helper function. Let's work on the second helper function. This is the most interesting part of our algorithm. We're going to start by defining a global reference to the current ant, because we're going to need to modify it, and a global reference to the direction, which I guess we don't really need down here, so I'm just going to get rid of it there. We're going to ask if the state of the current ant is 0. If the answer is yes, we know we need to turn in a clockwise direction. To do that, we're going to update the value of the index in direction by adding 1 to that index where the number 1 is located. Remember that those indexes look something like this. This right here would be the direction right. To make it go 90 degrees in a clockwise direction, ending up in the down direction, we just need to take this one and move it here. And from down to left, we move it here. and we repeat the process. However, notice that to go from up to right, we need to use the modulo operator that will allow us to wrap the last element to the first element, completing the circle. This is going to be done in 3 steps. We're going to generate a new local variable called new1position, because it's the position of the number 1, and we're going to take the direction and we're going to ask for the index of the number 1. Then we're going to add 1 to it, and after we calculate that number, we're going to apply the modulo operator that is going to receive the number 4. So what the modulo operator does is respecting the identity of the numbers as long as those numbers are less than 4. So 1 modulo 4 is going to be equal to 1. 2 modulo 4 is equal to 2, and so on. But 4 modulo 4 is equal to 0. And 5 modulo 4 is going to be equal to 1. So you can see how everything gets wrapped around these numbers from 0 to 3, which is 4 digits, matching the indexes of the elements in the list dir. So now that we calculated the new position, we need to set the new direction to be a list made out of zeros. We basically want to get rid of the previous one. We're going to say 0 for I in range 4. That is going to give us an array made out of zeros. So we're just overwriting dir. And finally, dir at the new index called new1position is going to be equal to 1. That's the new position. But this is only if the current ant is at the state 0. Otherwise, we copy these 3 elements, and the only change we need to make is in the plus. This plus will become a minus because we want to go in a counterclockwise direction. However, the rest of the process is the same. We still need to redefine the direction as a list of zeros and then assign that new position the number 1. We're almost done. Next, we're going to make the ant move. To make the ant move, we're going to use the coordinate system given by the rows and the columns. Here is a demonstration. If dir is equal to dir r, it means that the current ant will become the neighbor to the right, which is that neighbor in the grid at the same row but in the column that is plus 1. So the current ant will become the grid at the position of the current ant's row and the position of the current ant's column plus 1. We repeat the process, this time going down. We're going to say dird, and this time is going to be r that is going to get a value added to it. Rows increase vertically. Rather than the standard mathematical system that we usually use in school, the y-axis is flipped. It is inverted. To add to it, you need to go down, you need to add to it, and to go up, you need to subtract to it, with the value 0 being the highest point in your screen. So that's why we need to do plus 1 here. We copy again, and through the magic of video editing, I'm gonna finish this. Okay, so I didn't make a lot of changes. Notice that in this algorithm we are not using the diagonals. It seems that this function, it doesn't have the right name, so this is update dir. There we go, and let's run this program. Let's see what happens. And that is Langton's Ant. Now it seems to be working fine, but as soon as it touches one of the edges, you'll see that the program halts. So let me show you what the problem is. If I make the dimension something like 16 by 16, for which I'm gonna need to make the resolution really big so that we can see anything at all. Look at what happens. The program runs for a little bit, and after touching the first edge, the program halts and breaks. The problem, it says, is that there is a list that is out of range. Because we're trying to access, oops, let me see this, there it is. So because we're trying to access the coordinate of the neighbor that is to the right in order to go to that neighbor, looking at from the ant's point of view. But if you're in the right edge, there is no right neighbor. The best option is to wrap our world around itself, creating something known as a flat torus. So to fix the problem, we need to use the modulo operator whenever we see the plus signs. Python is quite permissive in this area because it automatically uses the -1 as the index representing the position of the last item in the list. However, the plus symbols have to get wrapped around this modulo. So let's select this, let's add the brackets, and let's add the percentage symbol and the length. Now we need to use dimensions at index 0. Because this involves the columns. The columns are giving us the first item in the tuple dims. And we do the same thing for the rows. This time, we're gonna use the percentage symbol and we're gonna use the length at dimensions 1. That's it. If we run it this time, oops, this should not be len. Okay, there we go, because it is already an integer. Okay, let's run it again. And this time you can see that even though it looks quite messy, almost random, because there is no resolution, the program is working. As soon as the ant finds itself at the right edge of the screen, it teleports itself back to the beginning. So this implementation, as I mentioned before, is interesting because it demonstrates the simplicity of an algorithm that creates complex patterns in this case, and that is what we call the emergence.